Yeah, well, good morning also from my side. I think if it's this little audience, so maybe we can make it a little bit more interactive than, and not really like this typical presentation style, but maybe make an open discussion about the nice topic of trusted computing. And I guess you all have heard about trusted computing, so that's why you're here. Good. So, and what the idea is that I want to introduce this morning is to make this concept a little bit more proactive. So, at the moment, the state-of-the-art trusted computing is more or less a passive technique. So, the operating system interacting with a trusted platform module, and we actually want to make it a little bit more proactive, and we want to use it actually to supervise the integrity of a running software, not only looking at the integrity of files and BIOS as we do it so far, but also use it during runtime. Well, that worked a second ago. Let's take the right button. Okay. Yeah, as the term trusted computing already indicates, everything is about trust. So when we talk about system integrity, we have to talk about trust. So when we talk about trust, it is first of all, we have to trust in someone because we buy a hardware we don't know what the chip manufacturers might have built into the chips, so we have to consider integrity of the hardware. We also have to trust in someone when we consider the software, because everything we install and we buy commercial off-the-shelf software, it starts with the operating systems. We don't know what Windows is actually doing in the background. We don't know what our Word is doing, and maybe they're built in a flight simulator into Excel. Actually, they really did. Same thing applies to all kind of drivers that we install when we buy additional hardware. What we might download from the internet somewhere, public domain software. And okay, I called it the decentralized backups, also software I got from somewhere just to test or to whatever a friend gave me. So I never know what's inside this software. Okay, that's the one story. Oh my. No? Ah. Okay. The other side of the coin is, of course, I have to trust myself. And this is especially now when I'm using my systems and when we talk about computing. This is, first of all, I have to trust my own. This is laser, isn't it? Yeah. I have to practice this. I have to look at the software I developed myself. So this was actually meant to be addressed to the developers that are here, because actually it always depends. If I properly design software, if I properly develop software, it might be good quality software. But I know a lot of software houses and also other companies who just program this, program that, have a script file here, have a batch file there. There is no quality management. So the quality of our software is very important. Can I trust my own software? Or is it faulty? Or is it vulnerable? Same goes with the operational integrity of my system. Are my systems maintained properly? System administrators, are they doing a good job? And then there is, of course, this big pillar of malware. Everything we know, there is millions and millions of malware out there nowadays, and we have to see that we keep this away from our systems. And this is not so easy, obviously, but because how do we find malware nowadays? Antivirus software or something, which is usually simply pattern matching. But our antivirus systems, they don't know all the patterns that exist out there, because 100,000 of patterns are added every day. And how often do you update your database? Maybe you even do it every day. But this is always running behind the running sheet. So
it's getting to the point where even malware is getting uniquely created for each target.
Yeah, that's the targeted malware attacks. Yeah, I will come back to this a little bit later. Yes. But indeed, this is one of our biggest problems nowadays. And this is the other problem with it is, if we talk now about this unique malware, or also if it's mass production malware, the sample databases are simply getting too big. So once a malware hasn't been seen out in the field there for a while, the antivirus vendors, they simply delete it from the database, and once they see it back again, it might be added again. But so it's always worth a try to try your antivirus system with an old malware sample you might have somewhere in your drawers, and you will see it might work again. Just not after months, maybe already, not even years. So what was trusted computing designed for? It was designed for this big pillar, trust in someone. So this is the core principle is quite easy. So we build a chain of trust from the BIOS through the kernel to the application, and everything we have gets a digital signature. That's the principle of trusted computing. And that's quite easy. So this is a whitelisting approach. So we have a certain set of software which we have installed in our system. We trust in the vendor that the software is stable and has a certain integrity. And then we sign it, and then we can just check the signatures. Is this still the same software? And the monitoring is done by this hardware module, the trusted platform module. Okay, that's what you all know. So just to see this as an example, so how does this chain of trust work? Okay, I took the top-down approach. So from the view of the application through the environment, it goes through user land, through kernel land, and more or less ends up at the hardware abstraction layer at the BIOS level. You can also interpret, of course, that you should trust in Fraunhofer. It's also a good interpretation. That was the advertisement part. No, of course. No, this is in principle how it works. Quite easy. So the problem so far is that this chain of trust ends somewhere. Where does it end at the moment? When we load an application from the hard drive, from wherever it is, from the internet, into the memory, so in the volatile memory, it is not protected anymore. So any process which is initiated from a file or something, once it's instantiated, it's not under control anymore. And this is actually the big risk. So this signature thing that works at ROM, at file level, everything, I can build a checksum on. Actually, I can do this in the memory as well, but it doesn't make much sense because it's permanently changing. So that's why the big risk nowadays is infiltration by exploitation or bugs, faulty software that might cause different, similar problems. So where is the problems? There is a challenge. So our challenge here is to identify exploitation. And now we move to this trust in myself pillar. So where do I need trust? I need trust, first of all, in my own developments. How can I solve this? This is easy. Testing, that's the easy thing. Focusing on the correctness of data, just trying inputs, so at the different levels, from module testing, level 2, level 3 testing, to system integration testing. This is how it's usually done. That's all what you know. And control flow graph is then more the static analysis. I can do the static analysis of my system, see how it works. Trust is also required for system maintenance, of course. This is now addressing again malware and bad configurations. This is why I need patch management, configuration management, and of course I need good system administration personnel. Otherwise, I anyway don't have any fighting chance in this good and bad game. And of course, the third pillar, what we already started to talk about, is malware protection. What we usually do nowadays is we have firewalls in our networks, in our systems. We have intrusion detection systems, antivirus, etc., etc. Which is nice, of course, but it doesn't help us with the problem which we just stated, the exploitation problem. For this, we need explicit integrity watch. And this is what trusted computing is doing it at file and kernel level with the hashing. And what we need really is a kind of active monitoring during runtime. So this is actually the part this is missing and what I want to discuss with you today. So what is state-of-the-art integrity watching? More or less what's mostly done nowadays is what we call code block execution monitoring. So there is two big categories that we actually analyze. So this is, first of all, the code analyze. This is what's done by virtual machines. They look for critical instructions. They can sandbox certain parts. They can do code sanitarization, so that means replacement of critical instructions. And of course, this all works very good with deterministic behavior. Code analysis mostly focuses on the branches. So this is a code block, and a code block is followed by a next code block. And in between that is branches, go left, go right, yes, no, if, then, else, this typical statements, or a switch. So this is what we actually can create during compilation process, for example, a branch table. So where actually can my program branch to? The other thing what we usually do in software design is we design pre and post conditions to check if the code block is really executed in a valid context. Exceptions is also a nice thing, especially the Java programmers will know when they do the try-catch always. That's more on the abstract level. On the low level, it's exactly the same thing. So see what kind of exceptions can occur, where they occur, and why they occur. The other side is the statistical methods. This is analyzing code from its behavior. This is not really reliable, but it gives some certain indications if all of a sudden the behavior of your system is changing. This is about use of instructions. So in a typical code, 90% of your instructions are move instructions. So more or less. So if this changes and it's only 60%, then something's definitely wrong. So this is not really code then anymore that you would execute. This is something a software factory compiler would produce. Sequence of instruction. Yeah, there are usual sequences and there's also suspicious sequences. Branches not taken, not taken. This is already nowadays in branch prediction tables inside the chips, but also virtual machines look at this and see if all of a sudden some program parsers are taken more often than others. You can continue this list. So this is not a full list. It's of course you can look at operation system calls, inter-process communication. Communication at all is a process communicating usually or not. What are my communication peers, and so on and so on. And on the implementation, if you look, for example, at a virtual machine, then you usually run something like a security agent. So this is a typical monitoring a security agent looking at the control flow, as said, either doing static analysis, looking at the code, doing the code sanitarization, or looking at dynamical analysis, branches taken, branches not taken, and then can give us a feedback. But this only works with a process which runs under a kernel level. So then we talk about hypervisors, we talk about virtualization at very low level. So now I'm just asking a question because we are such a little audience. Shall I more focus on the technical details, or shall I more focus on the concepts? Because who wants to know more techniques?
I have a question to that. I mean, we're writing a virtual machine, so if we find a branch that has never been taken before,
yeah.
What does that tell us? Does it tell us it's insecure to run it? Should we stop running it? What's the approach here?
That's a good question actually, because I cannot give you now a definite answer. This depends on the context and your interpretation. Of course, if it is a valid branch, this part of control flow was designed to be taken at some point. If this never happens, and then once it happens, and then never again, then the question is, of course, I would at least analyze. So why has this been taken now? This is maybe not suspicious. If this never happens, and then it happens all the time, then something has definitely changed. So then I would definitely maybe even halt operations and have a look. So what is now happening here? So, but there is no final answer to this question, because it really depends on, maybe you have changed something. Usually you see something, you changed something in your system. And really we talk now about ultra tactical levels. So this is really, I wouldn't really go on one branch. I would say it's the entire picture that changes the picture. So, yeah. Good. So what will be the future? So now we talk about the next generation of integrity watch. This is this big buzzword, control flow integrity. This is now really monitoring a program during execution. We can do this in a virtual machine. Our approach will be to do this at hardware level. This is now really checking of code blocks and control flow in the context. So supervising the branches and seeing if all of a sudden a branch goes somewhere where it shouldn't go. So actually what I need for this is the entire picture. What are valid branches? and what are branches that are not foreseen. And this would be exploitation, because this is something that you cannot really, that you did not plan during your process. So what is actually happening? You're compiling a program, or it's dynamic binding, it doesn't matter, it depends on where you come from. And at the moment of compilation or at the moment of binding, you know the context, you know exactly this graph, you know all legal and valid parses. The problem is, at the moment, we throw away this information. We don't use it anymore. After compilation, it's gone. So the approach we follow with trusted control flow integrity, what I want to introduce in a minute, is that we don't throw away this information, but keep it as a metadata. So we can store this in a portable executable header or in an ELF header, talking in the Linux world. So we keep this information. And when we initiate a process, so when we take this from the exe file, bring it into the process memory space, initiate the page file, so copy the code onto the page file, and then copy this metadata into the trusted platform module. So there it's encapsulated and safe. So, and then in the TPM, whenever a branch is coming up, we just check, is this a branch which leads into a code segment which is foreseen, or does it lead somewhere else? And especially in this moment, when I branch somewhere which has not been defined, this is definitely an integrity breach.
How are you going to validate the chain of custody of that and make sure that it's never been tampered with since it was created, the metadata?
Can I talk about this in a minute? Very nice. Because first of all, okay, what are we doing at the moment? Not much. We try to defend it with this kind of antique methods that we have already, but this is how it feels. This feels like the medieval knight trying to survive in a digital world. Not very efficient. Okay, so now going back into the concept. So the idea that we want to promote here is to actually have a wedding between those two concepts, the trusted computing concept and control flow integrity, to make him a little bit more happy. So he's smiling already. I don't know if you see the difference, but he's now smiling a little bit, the tux. Yeah, okay, well, have a look at those tables. So this is a typical branch table, which is a if then else statement, true false binary decision. So you see branches going from a specific address to a specific address. This is now whitelisting. So here we start a jump which goes to another address, ends up here. So this is how it works. We have an active side and a passive side. The thing is, we have transfer control flows, control flow transfers that are static, and we have dynamic ones. So static branches, procedure call. Static branch from one code block to another, and then the dynamic ones is, for example, returned from a function call. We will see this in a minute. Or switch case, for example. This is also dynamic. Or in the object-oriented world, when I just create an object, I don't even know how many objects I will have, because I keep creating. So the class, the methods themselves, they will also always stick to this class object. They will be constant, but the data structures and the dynamic parts, they will be always in a different memory position, which makes it a little bit more tricky, but not impossible. It just needs update. So let's see this at the example of a static branch, because this is easier in the beginning. So this is quite easy. We have some, this is this if then else statement, quite easy. I think as a software designer you can recognize this, right? Maybe. You're familiar with low-level programming? A bit. Yeah. I asked you if you want to go tech hardcore. Here we go. No problem. The funny thing is, so, okay, this is now the active table going here. You see from which address to which address we have the branch. So that means from 3D, we can branch to 4F. At the other side, we see if we arrive at 4F, this jump can come from 3D or from 4.3. So, and if you create the entire picture of the program, then you will see all of a sudden, oops, it's the same. So this is a tautologic approach. If you just take all the branches defined in your program and on your page file, you will see, oh, this is the same table. And this makes it, again, easy for us to collect the data, because then this is what we can see during compile time. The program is created, and these branches are created by the compiler. He knows the delta from one address to, so the branch short. He calculates it, so we definitely know these addresses. And we can take the addresses, put them to the header file. And from the header file, before the process manager the first time branches into the process, it will store the information into the TPM. And then TPM is in control. And whenever a branch occurs, the TPM will be consulted and check, okay, is this now a valid branch or not? And by that, actually deviation in malware is not possible anymore. Exploitation is killed. Dynamic branches, as said, a little bit more complicated, so that's why we can go through this a little bit more in detail. So this is a code snippet. Now it's a typical translation of a switch case from C++, for example, into assembly code. So it would work with putting addresses to the stack, and then he just jumps to the pointer on the stack, which is then an address where it would actually jump to on a specific switch case. So all the addresses are put onto the stack, and from the stack it then jumps to the different code blocks, whatever the switch case statement, whichever case is selected is the true case. Same would apply to return from function call. So it's exactly the same system. So if we look here at address, so this would then be the start address of the code block. I think I did. So how do I do this integrity check now? Looking at the stack, I know the addresses. So when I look at the ESP is now at the address where I want to jump to. So, and I know the address where I come from because it's my current program counter. So I can push my address to the stack, and then just this is now added functionality to the TPM library function. Then we now just call this check branch function, and both is on the stack. Now both the address where I come from and the address where I want to jump to. This is very easy. This is what the compiler will actually add now in code. So it is 8 bytes per branch. So, and we did an analysis, so the maximum an executable can grow to is something about 28, 29. So it's less than 30% of additional resources in terms of space we would require, including already the extended file header, so the ELF or the portable executable header that needs to be extended. So the TPM function call is executed, and now on the stack we have exactly this pair which we need for the branch table. So where we come from, where we want to go to. And then the TPM is just called because it's still passive, and then the TPM just compares this couple from the stack. That's exactly what the function is doing, pulling those things down, doing this function call to the TPM, and then the TPM can evaluate against the stored branch table, is this a valid branch or not? And if not, then we can terminate the process, halt the process for forensic purposes, just stops the process. Question?
But how do you know that the address on the stack or the offset on the stack is a valid offset for that switch statement, right?
For the switch, you can pre-calculate it.
Yeah, that's pre-calculated by the compiler. Yeah. Yeah. That's a list of switch cases, and it usually goes through all the cases, case by case, and when the case is not fulfilled, the condition, it just pops the top element from the stack. This is how a switch works. So it puts everything on the stack, and then it goes through case. If case is true, then it jumps. If not, then it just pops. Next element.
But what kind of error can you avoid by that? Is somebody manipulating the stack, or somebody manipulating the code?
Yeah, this is a typical scenario for whatever. Here we talk about stack smashing, stack overflow, any exploit. We have to look at exploitation techniques. So this actually goes against exploitation techniques modifying the stack. So what exploitation does is it always manipulates some dynamic data structures, the heaps, the stack, whatever, in order to deviate a branch like this. The only thing how a malware can actually be executed when we have exploitation as the attack vector is that it somehow deviates the program flow to the malware. And this is very hard to do because we will discuss this in a moment. The page segment itself is read-only, so you cannot modify it from the process memory space. It's read-only. The only thing you actually have is that you can modify something where you can write to, which is heap and stack. So this is how, in principle, it works. There's, of course, some more advanced, fancy techniques but they still use that. You still need to use something what you can modify. Read-only is not an option.
But in that case, I really need to modify the stack.
Yeah.
If I modify the code itself,
Yeah.
if I could do that, then I would probably remove the
Yeah.
call to this check method.
Yeah, but you cannot change it. And this is the funny thing. This is why this chain of trust works. So the file itself, including this new enhanced file header, the portable executable or the ELF header, is protected by good old trusted computing. File is hashed. So then this information is shifted to the TPM. The code itself cannot be modified. This is why you will always have this statement here for the branch. The only thing is what you can modify is the stack. And what will happen, so this is compiled in, this is in the read-only page segment, so you cannot change this. It will always do this push, it will always do this call. So this is the 8 bytes which are actually added. So, and then it does the jump, but before it did this call. And in this call, it really takes those two elements, does the function call at the trusted platform module, and then either it's integer or not. If integrity is violated, then process termination, halt, whatever your consequence is. So this is what we left open. Our objective is really to see that this happened. And this is, okay, we started discussing this already. And this is why the text segment is not a problem, because it's read-only. Of course, it can be a problem. Nothing is really static. There might be security updates. There might be patches, some of them might be faulty or by intent malicious. Then there is all these debugging things, debugging mode changes some things, might be a little bit critical, hard to do, but not impossible. And then, of course, this entire re-engineering thing. So here, yeah, dynamic branches, this is what we just saw. Okay, we did not talk now about static analysis, but I think this is quite obvious. The problem is these modifications, which actually can deviate the control flow. And this is why, as we already said, the branch tables, this is whitelisting. This says what are good branches and what are bad branches. So, implementation so far, yeah, in software, we can build a virtual machine which is exactly doing this. This would be the security principle we just saw, just a little bit enhanced. We can discuss when we talk about OS enhancement that we look at the process or the process and thread environment block. Yes, was just missing the word. And yeah, of course, we have to see how to optimize things during software development. Yeah, we can, of course, do integrity checks at machine code levels, which are compiled into the code by the compiler. The same thing, if it stays on the software side, we can still exploit it because it stays in software. And the future that's what we are discussing now. This is really, okay, the next step already after trusted computing would be maybe an implementation into CPU. At CPU level, we can discuss, for example, extending the branch prediction tables and put this information also into the CPU. The question is just where to store it there. CPU space itself on the chip is very limited. And those branch tables can be quite big after compilation. As said, up to 30% of the code can be metadata. The problem is where to accommodate this in the chip, and you don't not have only one running process, you have 50, 100 processing running at the same time in your modern system. This is simply a question of capacities, of resources, chip construction. So we are not that far yet. I discussed this with Infineon, and they said, yeah, maybe in 10, 15 years, but we are far away from a practical implementation of this.
We ran into the same problem.
Yeah.
The security module within Intel.
Yeah.
It was the same problem. We ended
Yeah.
up with so limited space that we could not create oversight pages for everything.
Yeah.
You had to choose. There was not enough space to put everything.
Exactly. And this is why at the moment we see that implementing this thing with the help or with an extended version of the trusted platform module might be the viable option that we can walk now. And actually, there is also already, I don't know if you know, Data Warehouse and G&D. They are both kind of, we are still looking for a little bit of venture capital, but at the moment, they are already kind of ready to build this thing. We just look for the next 10 million or something, which we actually need to build the prototype. But we will develop it in software first, and then if we have enough persuading arguments, then I think we will get it going. Anyway, and of course, at the moment, things are still passive. The next step would be to make the TPM more proactive, so that the TPM can also send an interrupt. So at the moment, it's still, we have a function call from the OS side to the TPM. It's of course much more efficient if the TPM can work autonomous and then send a security interrupt to the operating system to hold the process. So at the moment being, it's a little bit still asynchronous. That means, yeah, I have this deviation into malware and see it, but by the time this process termination signal then really comes, because it's a passive function call, I still execute something like 10, 20 instructions of malware before the process is finally terminated. So it shouldn't hurt much, 10, 20, but your system is maybe in a compromised state, depends on what this 10, 20 things did. That's why our next step in the development, it's not part of this presentation, is that we will also use this for forensic purpose. That means that the TPM is enhanced by a trusted forensic module. We will look at the modules in a minute, and then that we take then the image, drop it to a forensic drop zone, internally or externally, and then we can analyze actually the process memory space. What has happened, why has it happened, and what has been executed and done. And 10, 20 instructions you can easily analyze and see, and from that you can actually see, has this now a consequence on the security of my system, on the integrity of my system? Okay? Very good. So this is how it looks like, the new layout of the enhanced TPM. So we just simply added one module here, which we call the attack recognition module, ARM. That's why arming the TPM. It's a nice wordplay. And this is actually how the layout looks like now. It's actually 4 modules, and the T4, the trusted forensic module, would be module number 5. So we will demonstrate this concept this summer. So this is actually the good old functionality of TPM, firmware and file monitoring. So this is we also put this into hardware just to make the process more consistent and also faster. Then we have this control flow integrity unit we just discussed. Then we have this, someone needs to operationally run all those things. This is the integrity supervisor unit that is actually triggering the CFI and does the signal processing. And that's brand new, more or less, a peer communication unit, because what we have done so far is local. So only me at the system, I get the process termination, malware is stopped. Still, something has happened on my system. So what this thing does is actually it sends a signal to a neighboring TPM. Yeah, do not trust me. This is now the step forward to a distributed trusted system. And so bringing this trust chain also to a network level. So now we have control flow integrity, now we bring it to the network level. So there is 2 basic problems. First of all, it is the racing conditions. So if the malware is actually doing 10, 20 steps, maybe doing some OS calls or whatever, it could, of course, also compromise my network connectivity. Very unlikely, but not impossible. So this is a risk, so I have to be very fast. And the other problem is man-in-the-middle attacks, of course. I can do combined attacks, also combining my connectivity and trying to isolate my system from my networks, or do man-in-the-middle attacks and try to intercept any communication with my peers, any warnings that there might be an integrity breach. So this is the 2 problems I have to deal with. And this is why we actually built the networks on a very low level, and we built the network between trusted platform modules. So in other words, everything between the TPMs we see as unsecure. So the implication is quite simple. We need a fast protocol and we need a secure protocol. Secure communication between trusted platforms. The implementation here is Diffie-Hellman. So we have the PCU, the peer communication unit, does a Diffie-Hellman handshake and we do that at layer 2, at ARP layer. We have a protocol we called Trusted ARP. That's an ARP extension, just doing exactly that. So it's the same thing as good old ARP, but we have this trust handshake in the beginning, key exchange of Diffie-Hellman parameters, and then we have a little bit of protocol extension doing exactly that, what I described, notification of security incidents and in both directions, as pulling and as pushing. Why pulling? Yeah, if my system is compromised and my network communication is compromised, maybe the traffic is filtered. So anyway, I send the ARP, but it's somewhere just discarded on the protocol stack and never leaves my system. So that's why, going back to the system, the protocol also has an active component that one TPM regularly asks the other TPMs, and we do this in 1 millisecond, but one ARP packet in a millisecond doesn't really hurt. It's just a keep alive signal. They're asking the other one, are you there? And there comes a reply. So once there should be a filter function in a malware being executed on a system, the other one will automatically see because he does not get the right reply anymore to his keep alive signal.
There's like a timeline where it's not seen for X amount of time to untrusted, or is it like...
Once it doesn't answer, it's untrusted, and I do this every millisecond. Jing, 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 jing. It's a permanent pinging.
Okay. And then how do you retrust it again?
Oh yeah, it's like the initial trust gaining. It's two-channel technique. So the first thing is, of course, Diffie-Hellman parameter exchange. So once the thing is compromised, we do ARP blacklisting, so the system is isolated, and then it's manual work. Actually, the operator has to check, bring up back the system, and then do two-channel authentication to bring it up. This mechanism is a bit more complex because it needs reliability. The easiest thing is you do it on the phone. I brought back the system. Yeah, I brought back the system. Plug in, and then it does a handshake. That's the manual thing. But of course, you can also automate this because in the cloud, it's very uncool to do everything manual. Okay. Yeah, that's Trusted ARP, and yeah, the idea is, of course, to extend this protocol a little bit more. If we want to do something like trusted forensics, then of course I need to digitally sign the image for this to make it court-proof. So that means the TPM will sign the image. The image it took from this memory space, so it needs to be copied from process memory space through the Trusted Platform module. The Trusted Platform module will sign the packets and then send it to the peer, and then the peer either on the peer I have a drop zone where to store it, or it will be forwarded. Then this peer acts as a forensic router. So somewhere I will need a forensic drop zone where to drop it. It's not finally researched yet, but we are working on the concepts. And yeah, that's the forensic functionality. By ensuring that it is layer 2. That's the reason why I'm always faster than any malware would be that has to run through the protocol stack. I simply take a raw socket and just communicate on layer 2. So as soon as I see the incident, and I don't even need to report back to the operating system because everything happens in the attack recognition module. So the integrity supervisor will immediately notify the PCU. The PCU will create this notification package and send it through the raw socket, and the raw socket layer 2 packet without all the rest of the protocol stack will be very, very fast. So faster than any malware can be that has to process its data through the entire protocol stack. This is why we win the racing condition in 100% of the cases.
Do you plan to pair or quadruple those chips in any scenarios where they'll be...
This information is a little bit confident. No, but of course there is ideas like this going on. Yeah, but the trouble is we are just opening a new Pandora's box, kind of. And yeah. No problem. Yeah. Okay. Yeah, and if we see this now as a network, so we saw now communication with a peer, and of course we can also see this in a hierarchy, so that by this technology we can of course implement this on each and every node on a local network. We can even think this bigger in entire network segments. up to the point where we could think this is a new communication standard we could bring up globally. So I think there are some players in the game that would not really like this idea, but
What's the network overhead then? Is there any network bandwidth overheads that you mentioned?
the overhead is ARP pinging, actually, but this is 1 packet per millisecond at ARP layer. It doesn't really play a big role. Of course, on a global view, it is something.
That's when I get into
Yeah.
VSAT communications and
Yeah. Yeah, but the thing is, it's only peer communication. This pinging only works between 2 neighbors. So, and then the next 2 neighbors, and then the next 2 neighbors. So it's not that he's pinging everyone, that he's still only pinging his neighbor. So it's always adding 1 ARP packet per millisecond to local area network traffic. Also at tier 1 level, tier 2 level, interconnection, wherever it works. And ARP is just, okay, ARP was now 1 example. Of course, you have to look at other layer 2 protocols as well. But
so this is moving from like your root authority, root of trust,
Yeah.
to you are the root of trust for yourself.
yeah, of course. Yeah, then the next thoughts then, of course, have to be, so how about the ISP levels, tier 3 to 1 up, and of course some, it should have some kind of certification authority system behind it, because we want to also use signatures, so we should have a certificate inside the TPM, which is encapsulated there, and then, of course, this should be signed by a higher CA, which is somewhere up the tree. So, and then but this is now when we think about national signature legal framework, something like this, a national CA that then gives certificates to ISPs, ISP giving signing certificates of subordinated ISPs, and then of course gateways to the public and private world. This is how it works. Okay? Challenges, last slide. Yeah, okay. Of course, we have not talked about implications in terms of seeing integrity in the wider picture. Of course, we can derive a situation picture out of this, an integrity picture. So far what we understand as a cyber situation picture is mostly availability-based. Now we can do this integrity-based. There is a lot of open question about the handling of the incidents, with what should happen with the process, what should happen with the data, the forensic we already discussed. And the trust re-establishment, how once something happened. In general, we need the trust on a higher level. That was what we discussed with the certificates, make it capable for certificates running the CA. We just discussed those things. Still, the open thing is, that's the left side, the trust in the hardware and software vendors. But at least we can see exploitation.
I think one of the challenges I came into doing similar research
Yeah.
is that when you get into hardware, is that when you need to update it,
Yeah.
that when you've got this trust yourself scenario,
Yeah.
updating it becomes a very, very difficult process.
Yeah.
Have you find any intelligent ways of running that process?
Our approach at the moment is more thinking the legal way. At the moment, software and the hardware vendors, they are not liable for anything. And if they are liable, they have good lawyers. So that's why this is a question actually of policy and of lawmaking, so that putting more responsibility to the hardware manufacturers, to the software vendors.
So they do more, more of the supply chain effort so they don't get...
Exactly. So they have to take over certain responsibility first in who am I, whose software is it that I'm using, and what did you actually sell me? You're liable for this.